morning. We're team number 2. This is our senior design presentation about design and evaluate a chiller plan for a baseline data center. As an overview of the project, we're going to talk about the standard of our design, the alternative design, final design, prototype construction, and we're going to do a cost analysis of both design, the prototype and actual design, and we're going to get conclusions and see the works. So for problem statement, we're going to design a chiller plant to cool down a baseline data center in order to ensure the security of the equipment. So project description, to design a low-price 36-ton chiller for a baseline data center for the performance of the equipment. For project motivation, being part of an ongoing research project of FIU and an ongoing research project funded by ASHRA is one of our first motivations. As project description, design a low-cost 36-ton chiller plant for a baseline data center, and also constructing a chiller prototype and evaluate its performance.
So nowadays, more than ever, data centers are the backbone of the modern economy. And due to the huge growth in data centers, their energy consumption is accounted to be 1% of the world and 2% of the United States total energy. Data centers can be actually cooled down by air or water. The air-cooled method is the most widely used. In order to do this, a computer room air handling unit is used, and this unit needs to work in conjunction with a chiller plant. The chiller plant is located outside of the data center and provides cold water constantly to the correct unit. There are several different types of chillers in the market, but most of them use the vapor compression cycle, which is composed by an evaporator, compressor, expansion valve, and condenser. So these are the standards to be used in the project. The first one has to do with the minimum energy requirements for buildings and equipment. Second one will provide manufacturers, engineers, and contractors designing procedures for chillers, air-cooled chillers, and testing. The third one classifies refrigerants into 6 different categories according to flammability and toxicity. And the ASHRA Technical Committee 9.9 provides thermal guidelines for data center environments. So this is our first design alternative, a water-cooled chiller. We didn't select this one because it was the most expensive one, because it uses a cooling tower, an additional pump, and additional piping. The other design, which is the air-cooled chiller, this is the one we selected. It's not as expensive as the water-cooled chiller, and it is also more stable than a computer room air conditioning unit. This is our final design in SolidWorks for the air-cooled chiller, and these are the major components. We use a scroll tandem compressor, a shelling tube evaporator, an air-cooled condenser, and a thermostat expansion valve. So our design strategy was to size and select components based on these design operating conditions given by the RE standard. Always taking into account that our cooling capacity needed to be at least 120 kilowatts. So for the evaporator selection, we use, this is manufactured by Alfa Laval, and we use manufacturer performance data to select equipment. As the table shown here, always taking into account the design operating conditions. So by linear calculation of this table, we have a cooling capacity without superheat of 122.8 kilowatts. So after that, we were able to size the compressor. This is manufactured by Copeland. We use the software selection tool from the company. Again, taking into account the design operating conditions given here, the software gave us at least 21 different compressors, but only this part number, this compressor, was able to provide enough cooling above 120 kilowatts. That's why it is used. The other ones were below. And this software actually gave us the mass flow rate of the refrigerant, the isentropic efficiency, which is really useful for hand calculations, and the discharge temperature of 99 Celsius, which is used for the next component, which is the condenser. This is manufactured by Gunter. This is a German manufacturer that also sells products here in the US. again, we use a software selection tool from them, and this was among the different condensers for these design conditions. This was the cheapest one, and it provided a total rejection heat of 180 kilowatts. This is taking into account the cooling power, the heat removed from the data center, plus the actual heat coming from the compressor. And finally, the thermal expansion valve. This is manufactured by Danfoss. And by, again, taking into account the design conditions, we selected this one, the TG4040. And this one has a maximum capacity of 153.7 kilowatts, which is more than enough. So this falls within our operating envelope. So after selecting all of the major components, we did some hand calculations of the thermodynamic cycles. These calculations are really long and tedious. They're shown in detail in the report. Here I'm showing the temperature versus entropy graph and all of the different states in the real vapor compression cycle. And in here I'm showing the different thermodynamic properties, temperature, pressures, enthalpy, entropy. For more intensive properties, you can find those also in the report. But by having mainly the defined properties, we can use these enthalpies and these formulas here to calculate the actual cooling capacity, the compressor, and the work in the compressor, and the cooling capacity using superheat or without the superheat, and the coefficient of performance. In order to double check those kind of calculations, we also decided to use another software for the simulation of the real vapor compression cycle, and we have these results. If we compare these results to the aforementioned table, you're going to see that the values are pretty much the same. We're going to have a small variation because for the hand calculations, we use the thermodynamic properties table given from the manufacturer, which is DuPont, and this software actually uses another source. It is a code called ReefPro that is made by the National Institute of Standards and Technology.
This is an internal flow simulation for the suction line and discharge line. This is the pressure scale, which red means high pressure. And we did this simulation by defining boundary conditions that were static pressure and inlet mass flow rate. This is the liquid line, the pipe that goes from the condenser to the thermostatic expansion valve. And here we have a table of the pressure drop calculated in 3 different ways. Hand calculations using software and SolidWorks simulation.
So here on this slide we have one of the most important points of our project, which is the price of the chiller design. Involving the operator compressor and all the components that my colleague said before, we end up with a budget of $24,000 for a chiller design, which is comparing with a JMA chiller company on the market that is $40,000.
So, as Kamal said, our initial capital cost is lower than the alternative. However, it is not a good idea to take that into consideration in order to decide which is the best one to buy, because this type of machines consume a lot of energy. So we have to take into account the cost of the energy consumption throughout the life cycle. So we do the life cost analysis. The alternative by JM Chiller gave us an ER rating of 10.4. This is the energy efficiency ratio. And our energy efficiency ratio was 10.03. So clearly, as you can see, our chiller is less efficient than the alternative. Now, by having these numbers, we can actually calculate the energy consumption per year. Here we are assuming that the chiller, which is going to be used for research, is going to be operating for 8 hours, 5 days a week, and 52 weeks per year. And also the energy cost is 10.77 cents per kilowatt hours here in Florida, according to the Department of Energy. So by having this useful life and an interest rate of 7%, we can calculate the present worth cost of both alternatives. So after this analysis, the present work cost for our chiller is still lower than the alternative. So based on these numbers, we can say that our chiller, our design, will be the best, the best option economically, because not only has the lower initial capital cost, but also the lowest present work for the life cost cycle.
So as a preliminary overview, for us constructing a prototype gives us a better idea of how we'll be constructing the real design. So this is here we got a CAD design of our prototype, which basically are the same components as the big one: compressor, operator, condenser, and a fan for cooling down. So for the prototype construction, once we get all the components from different manufacturers, we proceed to link the components by copper tubing and welding and put it all together, and at the very end adding the refrigerant tool system. So here we got a small video of the testing. So here we can see a digital thermometer that shows the temperature there is on the rocket. This should be the temperature coming from the data center, which is 12 Celsius degree. There is the rocket where we're going to receive the cold water from the system. Now we turn on the system, and on the blue bucket is going to be a pump that's going to be charged to pump the water through the system. So with that hand, we're changing the digital thermometer from the water at 12 Celsius degrees to the water that's going to be coming out of the chiller. So if you can see, once we put it there, and when the chiller starts pumping the water out, we're going to show on the camera again the temperature, the digital thermometer showing how the temperatures are coming down until it reaches 8.5, which is going to take a while. So here for our testing results, as I said, the water in the chiller, we use 12 Celsius degree because that one, the water supposed coming from the data center. We got a delta K, like an average of 3.5, that gave us a coefficient of performance, an average of 2.7. And with this number, we can get that the cooling capacity of the prototype was 260 watts around. So here we got a cost analysis of the prototype. Basically, the main component was the most expensive things. At the very end, we get a $783 cost for a prototype.
This is a chart showing the progress of the team, and here we see a chart of responsibilities which shows how the tasks were distributed among the members. For global design and perspective, we want to provide users manual in English and Spanish, and we want to offer data in both international system of units and English units, and develop data center standards depending on the outcome of this research, which is funded by ACRE, in order to implement them in the world and in the USA and eventually in the world.
So as a conclusion, putting components together and designing your chiller by itself, it will be a better option than buying a chiller from the market. And also constructing a chiller will always give you a better idea of how we are constructing an actual design. So for future work, we would like to construct the actual full-scale design that's going to be here by you, and we also like to do simulation for the frame that will be outside for extreme conditions. Any questions?
I guess I'll start with you. In your selection areas, you used software that was developed by Gunter and Copeland. Did you do any hand calculation of their calculations to verify that the output that they've produced that you're using as a decision maker is real?
For the simulation?
Correct. For the selection. In the selection, you used software that said this is the right machine to use. This is the right component to use. Did you do any confirmation that what their numbers were real?
Well, we did hand calculations, but when using the software, we only got the result from the software, and then we compared our hand calculations with the software results.
You did do that?
Yeah.
Okay. Okay, and then I'll ask you the question, fellow in the middle. In your analysis of the design, did you take into account vibration?
No.
Not at all?
They take into account vibration. However, the chairs in the markets, they have options to put vibration dampers at each corner, and also to use flexible lines in the connection, mainly compressor.
But is that in your design?
No, we didn't do that. It was something additional. We will add cost a little bit. But when we're comparing our costs to their alternative, they don't have those issues either. It's something additional.
Wouldn't you think that would be important?
The thing is that we didn't have any more additional manufacturer data for the vibration. We don't know how much it vibrates. So actually, if we design this, if we buy all of these components and we put it together, maybe we can have a better idea and then determine if it's.
But couldn't you have done the vibration analysis to figure out what a system like this would vibrate? To know where you felt?
We didn't do the analysis.
Okay, thank you. Great, and then last question. On there, you presented a table. Could you put back up the table that has pressure drops? No, it was three different methods for determining pressure drops. Yeah, okay, but somebody.
This
That's
one?
Yeah, okay, and you've got hand calculations, you've got the Danfoss, and you've got the SolidWorks, and they're all different.
Yes. Yeah.
What did you do to determine which one is right or which one was the best?
Well, actually, we know that, for example, the Danfoss software, they don't use the potential energy in the calculations. So that's why this number is always less than this one and this one. And in the hand calculation and SolidWorks simulation, we use the coefficients from the actual book, the fluid mechanics book, and the SolidWorks simulation may not be exactly the same, so that's why we see a small difference in the numbers.
So which ones did you use, actually? Which measurement did you use?
The ones we're taking on are the highest. However, the pressure drop is insignificant. The highest pressure drop is in the liquid line, and it doesn't really matter because this is the liquid line. It's not connected to the thermal expansion valve, and the purpose of that valve is to lower the pressure a lot. Like 28 bars lowers the pressure. Over here, it's just 0.14 bars, so it's insignificant.
Okay, thank you. And then my very last question for you is, in your life cost analysis, did you account for maintenance?
No, we didn't. Actually, we didn't put into account because we think that from the manufacturer it's going to be the same cost. That's why we didn't put them different.
Yeah,
Differentiate for the other ones.
we're assuming the maintenance for our chiller manufacturers are going to be similar numbers. So the main differentiating factor was the energy consumption based on the efficiencies.
So at least you should have put in it as a steady state if you thought that they were going to be the same.
No, you know, you
So it should have been in your
The
calculation.
reason we didn't put it because it goes up on another chiller, it goes up the price for us.
Okay, thank you.
How did you determine 36 tons?
Oh,
Right in the beginning, you began with something.
I mean, that was like the specification gave for us, but as well with 120 kilowatts of the research, and for we did the 35 at the calculation, we got 35 tons.
the cooling capacity of the chiller was given to us, and that is coming from the data center cooling needs.
So you don't know what the square size of the building or the heat that was generated by the computer
we
or.
have an image of the design of the data center. And this is the design, this is the crack limit, this is what will be receiving the cold water. and providing cold air. And these are the racks. The way you do this calculation is to take into account every heat source. And by adding the power ratings, you get that number. But that number was given to us.
Okay, because I have a building and I have 40 machines in it, and on a cold day in Florida, after we turn them on in the morning, an hour or two later, the place is warm. You know, and so the calculation is based on the size of the building, how much I have to air condition, how many machines I have in it.
Well, in this case also it depends on what equipment's in there, because if you got blade servers in there, they produce more heat than just 1U rack or 2U server. So I don't know if you looked at the worst case scenario, fully loaded with blade servers producing X amount of kilowatts per hour on heat generation, and then go by that, right?
That is the maximum.
And a lot of the data centers are not fully deployed anyway. They'll have empty racks and all that all the time. So you did that.
So for your live cost analysis, you said that the data center was going to be running for 8 hours a day?
Yes, it's only for research. This is going to be here at FIU. It's not going to be run 24/7.
So, what happens if I leave a simulation running overnight using the data center?
Well, according to what we were told, they're just going to be doing testing and measurements when they're in the lab, and that's the only time where they're going to be using the chiller.
Okay, it's curious because the data center usually that requires a cooling system because you're planning on using it for an extensive period of time.
That's for a real life application, yeah.
That would break your cost analysis, right? If it's anything more than 8 hours a day.
Yeah, absolutely.
So I think that your numbers are too close to definitively say that your design is much better. So I would probably dig deeper into those requirements.
Now, this equipment is off-the-shelf components, in order to get assembled components. So if there's, going back to the maintenance question that Sid brought up, that anybody could repair that then? Any technician could go in and repair it. If the compressor breaks, they can measure the pressure, they'll be able to repair it like any other system.
Any refrigerant technician.
It's not like a custom built anything.
No.
Did you guys consider instrumentation for your system?
When we selected the condenser and the compressor, the codes came with the control system as well.
Do you have some way of displaying that information to a user that isn't technically savvy in HVAC systems? Do you have a way of displaying like the temperature outlet, or the outlet temperature of your system? Because it would be really bad to not know that your system failed until your server's fried. And that would be a very expensive.
You mean like a digital?
Yeah, like does your system in the future?
No,
account for
we don't
that?
have that in the future.
Well, there should be redundant systems anyway, so there should be more than one unit in there, right?
Well, it only has 2 compressors, and it is not a dual system. Real data centers, they do have redundancy.
Yeah, I do a lot of work with data centers, and they have multiple systems and
Yeah, they
4
always have
or
backups,
5
yeah.
systems.
They got backup systems.
Yeah, and they're all able to maintain, even if you're down to one, it'll be able to maintain everything. So you got a little bit of overkill. So did you use like a factor above your maximum requirements to go over? For example, when you were doing your calculation for how many BTUs or how many tons to use, did you just go by the maximum use that? Did you multiply by a factor to make it
Well,
like
the
20% more?
maximum will be 120 kilowatts, and our actual calculations will give a maximum of 131 kilowatts.
About 10%. That's 5% more.
Those calculations are ideal numbers, right?
They're real, based on the performance of the equipment.
So, but those are given to you by the vendor telling you that the equipment should work like this by itself.
At the design temperature, at the design operating conditions, yes.
Okay.
As far as the proof of concept markup that you did, I see that you used 134A versus the 410 that you're actually doing in your simulation. What correlation did you get between your calculation simulations done on a 410 system versus your 134A? Can you speak to that?
Well, for the full size scale, at the beginning we planned to use 134A, but we couldn't find compressors that were capable of providing the capacity of using that refrigerant. So by using 410, which is like a high pressure refrigerant, we were able to have those capacities. Now for this small design, 134A was the way to go.
But you didn't, using that 134A, if you get a 70% efficiency rate on your simulation using a 410 system, here, did you get close to that based on the numbers with the new gas and the 134A, which is a lower pressure and so forth?
Actually, when we calculated the coefficient of performance for the full scale was 2.7. For this one, it was also 2.7.